right, here is the week for Precalc. We have a lesson Monday, Tuesday. We'll review Wednesday, chapter test Thursday, and then there's a lesson, no homework on the Friday. And here's my email if you need to get hold of me. Again, if there's any calculus students joining us and you need to pass, you just need to make sure you do all the notes and all the tests and make sure you get it to me somehow, whenever. So that might be in June or July. Somehow we got to get it to the school and get it to me so I can change your grade. But you would have to do all these lessons, show me that you did all the lessons and the tests. All right, let's get started. 22I. All right, we are continuing. From last week. We have 40 students, 34 like bananas, 2 like pineapple, 2 dislike both. Pick one. What's the probability that they like both? All right. There's going to be 4 questions here. So what might not be the worst idea is to make a Venn diagram. That should help you answer all the questions. You don't have to make a Venn diagram, but I think it makes it a little easier. Bananas, pineapples. 2 dislike both, so we'll put that in the bottom. Now, to do the Venn diagram, we got to answer the first question. All right, how many like both? Okay, well, I think I'm missing something. 22 people like pineapple. Oh, I got 2. That should be 22. 22 people like pineapple. All right, so to find out how many like both, if we notice these 2 numbers are well above 40, so we want to add those up. So the likes are 56. Well, there's only 40 people, and 2 of them don't like either. So there are basically 38 who like fruit, or one of these fruits. So if there's 2 that don't like it, there are 38 who do like it. And these 2 numbers add up to 56. So we just got to find how many are overlapping, how much overflow do we have here. So we subtract 38 from 56, and that's 18. That's how many like both. Then we can figure out the rest of the Venn diagram. 22 like pineapple, we already have 18 here. So 18 from 22 is 4. See how these 2 numbers add up to 22? And then we could do the same thing with bananas. We already have 18, we need 34. 18 from 34 is 16. So 16 plus 18 is 34. To check it, these 4 numbers need to add up to the total, which they do. We could put this up here. We don't have to, but whatever. I just did. So now to answer these other, 3 questions, it might be a little easier since I have a visual. What's the probability of like at least 1? All right, so again, the denominator, whoops, I got to go back to the first one. I didn't like how I worded this. So probability, they're not asking for the number, they're asking for the probability So there's 18 people who like both, but the probability is 18 out of 40, which is 9 over 20. That's the answer to the first question. All right, probability that they like at least one. Again, 40 is the denominator. We can count these up. We could subtract 2 from 40. Either way, we're going to get 38. So there are 38 people that like at least one of these. And then we reduce that down to 19 over 20. Probability of liking banana given like pineapple. All right, whenever you have a given, that's going to change your denominator. So now the denominator is we're liking pineapple. So it's not 40 anymore, it's actually 22. Now of these 22, how many like bananas? Well, that would be this number in the middle. 18 like banana of the 22. And then we reduce that down to 9 over 11. And then letter D, probability of dislike pineapple. I use the symbol for given. That's the symbol, a vertical line. Like banana. So again, we have a given, so our denominator is going to change. Whatever follows the given is your new denominator. Liking banana, that's 34. Of the 34, how many dislike pineapple? So again, the Venn diagram helps me see this pretty easy. 18 of them like pineapple, so 16 do not like the pineapple. So it's 16 over 34, which reduces down to 8 over 17. Next example. In a kitchen or whatever, top shelf contains 3 rice and 2 chicken soup. Excuse me. The bottom shelf contains 4 rice and 1 chicken soup. You are twice as likely to pick from bottom shelf. And that probably makes sense. You are more likely to pick something that's easier to reach than something that's harder than the top. This is all given. Pick one can. What's the probability that it's chicken? So this one's a little harder. Probably want to make a tree diagram for this. There's going to be 2 questions, but the tree diagram is going to help. Now this is a little harder tree diagram. We actually have 2 events occurring here. We have to first figure out what shelf we are picking from. So if we are twice as likely to pick from the bottom, I'll just label bottom and top, that fraction has to be 2/3. Okay, 2/3 is twice as big as 1/3. If it was 3 times as likely, it would be 3/4 and 1/4. So the denominator would be like 1 more than whatever this word is. So that's how we figure out which shelf we're picking from, bottom or top. And then no matter which shelf we're picking from, we can either get a rice or a chicken. On the bottom shelf, the chance of getting a rice is 4/5. Chance of getting a chicken is 1/5. On the top shelf, the chance of getting a rice would be 3 out of 5. And then the chance of getting a chicken would be 2 out of 5. So we can multiply all these. Again, we probably don't have to multiply all of these, but 8 over 15, 2 over 15. Also writing down the outcomes. It technically doesn't matter what shelf it came from when I'm labeling these, but whatever, just to be consistent. All right, the probability of chicken, we look for anyone that has chicken. That would be these two, and we add those up. 2 plus 2 is 4 out of 15. And the last question is a little bit harder. Probability of taken from top given chicken. So on a tree diagram, given, if it works from left to right, we can just get the answer here, but this is a little different. It's given chicken. All right, so we're actually working kind of backwards here. So it's not as easy as grabbing it from the tree diagram. We actually have to use our formula because this one's a little more complicated. So our formula for given is the probability of A and B over the probability of B. If it's A given B. All right, so the probability of both A and B, both top and chicken, would be down here. Top and chicken, that's both. 2 out of 15. The probability of B, the chicken, well, we already answered that question. That's right here, is 4 out of 15. Could use a calculator, but the 15s just cancel out. So it's 2 out of 4, which is 1/2. And that's 22 high. (22J) is the last section of the chapter. This is on independent events. I've already been talking about independent events. So in some of these sections, things kind of overlap each other. Independent events is where one does not affect the other. One event does not affect the other. Therefore, if we say find the if we're talking about independent events and I say find the probability of A given B, that actually would be equal to the probability of A given not B, which it also would be equivalent to the probability of A. So basically what it's saying is it doesn't matter whether B happens or doesn't. I don't even need to know about it because these are independent events. For example, what's the probability if I flip a coin and roll a die, what's the probability of it being heads? It doesn't matter what I roll on the die, whether I get what I want or don't get what I want, or if I do it at all, the probability of heads is still going to be 1/2, no matter what the die roll is. So this is not something we would have had to memorize or anything, but hopefully it makes sense that the probability of flipping the coin has nothing to do with the rolling of the die. So we could just concentrate on the flip of the coin. A and B are independent if and only if the probability of A and B equals the probability of A times the probability of B. That one we would want to know for the test. Give an example. We toss 2 coins and roll 1 die. Again, it's a 6-sided die unless it says otherwise. Find the probability of a 5 or 6, and let's use the symbol. Two heads. All right. So these are independent events. The coin will not affect the die roll. So we can break them up. 6-sided die, the probability of getting a 5 or a 6, well, 1 out of 6 plus 1 out of 6 is 2 out of 6, which is 1/3. And means we are multiplying. Probability of getting 2 heads, we could act it out if we need to. Or we could multiply the first event times the second event. Either way, we get 1/4. And since these are independent events, we are just multiplying the 2 probabilities. Probability of a 5 or 6 is 1/3. The probability of 2 heads is 1/4. We will multiply to get 1/12. They may ask, and I think I already answered this question, is this an example of an independent or dependent event? Since one does not affect the other, these are independent of each other. Next example, the probability of A is 1/2, the probability of B is 1/3, the probability of A or B is some unknown number. Let's find P, this unknown number, if, again, we got 2 parts here. This one's kind of challenging. A and B are mutually exclusive. I'm actually going to write both questions down first. Maybe leave a line or 2. And the second question is A and B are independent. Now, if they're going to ask 2 different questions, logic would probably say, okay, these are probably going to be 2 different answers. So we do not do these the same. They look identical, look like they should have the same answer, but they won't. So we need to know what these words mean. If they are mutually exclusive, if you remember that, that means they have nothing in common. So again, remember what the problem is. In both problems, we are trying to find the probability of A or B. So let me just write that down so we don't forget that. So in both problems, it's an OR problem. You're trying to find probability of A or B. Now, if they are mutually exclusive, there's nothing to subtract. We can just simply add those together. So there is nothing they have in common. So that you can use a calculator. Basically, you got 3/6 over 2/6, which is 5/6. And with any of these problems, you could make them decimals or percentages if you want to. I always like fractions, but it doesn't matter. They rarely would say you have to write it as a fraction or anything. Actually, I can't even think of any time when they do that. So you could make these decimals or percentages if you wanted to. All right, now in B, it says they are independent. All right, so if they are independent, that means the probability of both is multiplying. So we first have to find the probability of both. So we multiply the 1/2 times the 1/3 to get 1/6. So that's the probability of both. Now remember what the original problem is. It's an OR problem. But if we made a Venn diagram for this, they are overlapping. Here's where the 1/6 would go. So we don't want to count that twice. So we need to subtract that 1/6 from the previous answer, basically. So we're going to add, so it's the probability of A, which is 1/2, plus the I can even write this down, probability of B, which is 1/3, but now we need to subtract the probability of both, because you don't want to count it twice. It's kind of like saying picking a red queen in a deck of cards. There are 4 queens, there are 26 red cards, so 4 plus 26 is 30, but you counted the 2 red queens twice, so you actually got to subtract the both from there. So we already know this is 5/6, so basically we are going 5/6 minus 1/6, which is 4/6, which reduces down to 2/3. So whenever you have an OR problem, we know we're adding, but we have to subtract the both. In the previous problem, there was nothing to subtract because they were mutually exclusive. So really you're subtracting 0 in the previous problem. All right, next example. They have 3, formulas, we'll just call them equations. I don't know if they're necessarily formulas. We have 3 equations, and we want to match these up with some definitions. So this is matching. Here are our 3 equations. Here are our 3 definitions. Mutually exclusive, independent. So this problem is pretty similar to the last one, except we're matching and neither. So as I've said kind of all year, I would always try to find the easiest one. All right. So I don't know, the one we just learned today is independent. Okay, well, let's find that one. So, okay, that's right here. All right, so independent goes with this one. Now we need to figure out what mutually exclusive means. Again, that means they have nothing in common. All right, right here. What does A and B have in common? Nothing. So that would make that mutually exclusive. This one looks like it should be something, but it actually isn't. It's neither. Last example. Two dice are rolled. Sum is X. Find probability. And there are 3 questions. X is less than 9. So we need to know something about dice. So we're rolling 2 dice. Again, it doesn't specify, so we know it's a 6-sided die. So maybe you know there's 36 possibilities because there's 6 on the first die, there's 6 on the second, so that's 36. Might not be the worst idea to write them all out. So like 6-6, 6-5, 6-4, 6-3, 6-2, 6-1. This wouldn't take too long. Or maybe you just do a little bit like this, and you just realize, okay, there's 6 in each of these rows. There are 6 rows, so that's where I can get my 36 from, even if I don't fill in the rest. So I know the bottom number is 36. Now I want to know how many are less than 9. Maybe I just write the ones that are bigger than 9 and subtract it from 36. So one way of doing it is circle the ones that are 9 or higher. Okay, these are 9, 9, 9, 9, and these. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there are 10 that are 9 or more. So if there are 10 that are 9 or more, there must be 26 that are less. I could do it that way too. I could have counted all of them, but either way, I get 26 that are less than 9. And 26 over 36 would be, what, 13 over 18. Again, these are probability questions. At least one die shows a 5. All right, so again, we know there are 36 possibilities. And I could, whatever, I'll just write out all the 5s. All right, so, whoops. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So these 11 all have a 5 in it. I know these don't, the ones I didn't fill in. So 11 out of 36. And the last question, find the probability of at least one die showing a 5 given x is less than 9. So they're basically combining the two answers that we just did. Since it's a given, we know the denominator is different. So instead of there being 36 possibilities, the given is it's less than 9. Well, if you remember from that one, there were 26 numbers that were less than 9. So we're looking at all the small numbers. Of those 26, how many have a 5 in it? So basically, how many of these are less than, the ones that have a 5 are less than 9. This is less than 9. There's another one, and that's 3. There's 4, 5, and 6. So again, those 6 are less than 9. So 6 out of 26, which is 3 out of 13. And that's that section. On Wednesday, we would do a review. Chapter 22 test. They all have multiple questions except the first one. Table of outcomes. That's where they give you a table. They fill in some of them, you fill in the rest. A lot of these kind of overlap. The whole test is on probability, so several of them will have tree diagrams, several of them will have Venn diagrams, several will have conditional probability, that's with the givens, several will do with dice, and this one isn't really a question, but there's several definitions that you need to know. If you don't know what mutually exclusive is or independent, probably would get those wrong. Then Thursday would be the test. So again, you can pause it to get the questions down. I guess I don't need that page. All right, so here's questions. And then here comes the answers. that's it. All right. On Friday, this one you might have to be a little patient with me. I actually don't have the notes in front of me, so I'm going to do this by memory. So this is something I just would have added. There's no assignment with it, but good to know.